In this video, we're going to do a couple more examples, finding tours with cheapest link, with the cheapest link algorithm. All right, so here we have K5, and we're looking for a circuit. So we want to find a tour that starts and ends at the same vertex. So the first thing we're going to do, I'm just going to make a little copy of this graph, but just the vertices. So I'll do A, B, E, C, and D. And now I'm going to scan the graph and see what is the cheapest edge on the entire graph. And I can already see AE is 1, and I'm not going to get any cheaper than that. So I highlight the 1, and I'll draw it in here. This drawing in isn't strictly necessary. You don't have to do it if you don't want to, but just for demonstration purposes. Okay, now I'm going to scan the rest of it. I see I have a 3. Do I have anything cheaper than a 3? I've got a 5, 6. Everything else is double digits, 8. So this 3 is going to be the cheapest one. So I'll draw this in. And so now, look, notice I have 2 highlighted edges connected to A. So I can't pick any other edges that are also connected to A. So if I want to end up picking this 6 right here, I can't do that. And I know these numbers are getting a little cramped. I'm going to try to write the numbers on the inside so that it crosses one of these lines. So the fact that this 5 crosses this BE edge, that means that that's the weight associated to that. So I can't draw any other edges connected to A. And similarly, I can't close off this circuit, BE, because I can't have any partial circuits, right? The only way I can have a circuit is if I'm closing off I'm connecting all of the vertices together. But once I have this circuit, I can't connect anything else because now everything A, B, and E will all have 2 highlighted edges. And so if I connect anything else to them, they'll have more than 2, and that will be a problem. So this 5 is out. Just like I said before, the 6 is out because A already has 2 highlighted edges connected to it. So my next best option is this 8, which is perfectly fine. It doesn't close off anything. Okay, and so I also am not going to be, my next best after 8 is going to be this 10, which I also can't use because it's connected to A. So that's also out. Okay, so then my next best is going to be this 13. But I can't pick that because B already has 2 highlighted edges connected to it. So then the next best after 13 is 18, which again, this would close off this circuit and leave D hanging. So I can't do that. And so next best after 18 is this 23. So I'll highlight it. That doesn't break any of my rules. Okay, and now I have a path, and to finish this path, I'm just going to connect C and D with this 28. And so my weight, so it doesn't matter where you want to start or end. You could start it at B, A, E, wherever. So I could do A, E, D, C, B, A, or I could do A, B, C, D, E, A, or I could start at any other vertex. But the big thing here is the weight. So that's going to be 1 plus 3 plus 8 plus 23 plus 28. So 1 plus 3 is 4. 4 plus 8 is 12. 12 plus 23 is 35. And 35 plus 28 is 63. Okay. And so I'll go ahead and highlight that. So this one was tricky because a lot of the edges that we wanted to highlight either closed off a partial circuit or connected more than 2 highlighted edges to one single vertex. 2 is fine, 1 is fine. You can't have more than 2. Let's look at a larger example. So this one's even bigger, but we're going to use the exact same process. So I'm not going to bother, just because this is so big, I'm not going to make a little copy here. Maybe I can make it down below. B, C, D, E, F. Okay, so let me find my cheapest link, my cheapest vertex, or edge rather. So I see I have a 2. So the question is, do I have a 1? I'm looking, I've got a lot of numbers to look at. I don't have a 1, so my cheapest edge is this one right here. So AF. Okay, what's my next cheapest? So I see I have a 7, I have a 5. Can I beat a 5? No, I can't beat a 5. So that's going to be A, D. And so just like before, we now see that we have 2 highlighted edges connected to A. So none of my other edges can involve A. So that means this 8 is out, this 30 is out, and this 12 is out, no matter what. I'm also not going to be able to do this 18 because that's going to close off this partial loop. So AD, that's going to be 5. Okay, so what's next cheapest after 5? Well, I see I don't have a 6. I think the 7 is probably going to be the next cheapest. So that's BC. That's not going to mess with anything, so that's fine. Now, my 8, like I said before, I can't do because this A is connected to A, but A already has 2 highlighted edges. So 8 is out. Now, it looks like I could do this 9 without any problems. Yep, that's not going to close any loops or anything or any circuits. 9. And it looks like I'm going to be looking for one more. So the next cheapest is 10, and I can actually do it. Because now I don't have a loop. If I were to do this guy here, this 18, that's a problem because that closes a circuit ADF. And so that's going to be the one I want. So this FE. Okay. And so my circuit, if I say I want to start it at B, then it would be BC, CD, DA, AF, FE. Or I could have it go the other way, start at E and go to B, doesn't matter. But my weight is the most important thing. So that's going to be 7 plus 9 plus 5 plus 2 plus 10. So that's going to be 16, 21, 23. So that'll be 33. So the weight is 33. Again, we don't know if this is optimal, but we do know that it's not as bad as it could possibly be because we're avoiding really expensive edges like this 30 or this 21. We're avoiding really expensive ones and focusing on the cheapest ones first. Okay. So hopefully you get a better feel for this algorithm. Once you get the hang of it, it's not too bad, and it's a lot faster than, say, repetitive nearest neighbor algorithm. Because for this graph, we have 6 vertices, so that means we would have to do nearest neighbor 6 times. So all these algorithms have drawbacks and advantages. But that's going to be all for this video.